Okay, let's go. So last time I left you guys with some examples to try. So let's actually get through those. All right. I think those were all of them. Okay, guess let's wait one. A, B, C, D. Okay. Someone tell me how to deal with 8. What did you guys do for 8? Yeah?
I'll try. First I isolated the trig function, and then
Okay.
I bounded by -1 is less than or equal to cosine of 1 over x minus 1 is less than or equal to 1.
Uh-huh.
And then I multiplied each side by x minus 1 cubed. And I flipped the inequality then.
So, yes, of course x cannot be 1, but for x not equal to 1, notice that whatever values this cosine gives you will be between -1 and 1 by our knowledge of trig functions. Cosine bounces up and down. And so you said you multiplied both sides by x minus 1 cubed.
Mm-hmm.
Well, multiply all sides.
Yeah, for that too.
Okay, and now?
And then I wasn't sure because I know sometimes you have to flip the inequality and make the less than's greater than's, but I wasn't.
Well, that happens in 2 cases. That happens if you multiply through by a negative number, or it happens if you're on the same side of 0 and you take the reciprocal of both sides.
Okay.
So this doesn't necessarily apply.
Okay, and then you can plug in the limit's taken to 0. No, it's taken to 1. No way. So you can plug that
So
in.
now, right, so now you apply the limit as, well, x approaches 1.
Mhm.
Okay, and then what do you get?
So then you plug in the 1 and you just get 0 on
Right,
either
so
side.
this side you get 0. This side, ditto. Right, okay. And on this side you get 0.
So then the limit must equal 0.
So the limit must be equal to 0 because it's squeezed between each one. So this implies that the limit as x approaches 1 of x minus 1 cubed cosine of 1 over 1 minus x equals 0. And then you say apply the squeeze theorem. Right. So that's how you would do that one. And so that's kind of one of the things you want to keep in mind here. Sometimes, besides the special trig limits like sine x over x equals 0 as sine x over x equals 1 as x approaches 0, and those other ones I told you, usually when you see trig functions, a nice thing to try to do is to use their boundaries that you already know about. So it is often useful to use the fact that you know that sine of x is bounded between minus 1 and 1, you know that cosine x is bounded between minus 1 and 1 from their graphs. In the situations where there are squares or even powers, you know it must be between 0 and 1. That might come in handy as well. So a lot of times if the special trig limit doesn't apply, a lot of times bounding your trig functions between known values, you know they have to be between these values. It gives you a nice restriction. Bounding them can give you a lot of help in computing a limit. So yeah, that was the squeeze theorem. And pretty much the first 3 examples were using the squeeze theorem. I gave you these 3 after telling you what the squeeze theorem was. So going through the next 2 examples should be very similar, so I guess I'll just kind of go through those fairly quickly. You guys will help me more with the other 3 set of problems. But a very similar approach would happen for B and C. So you know that if your x is not equal to 0, because in the limit we don't actually care about even being there, sine 1 over x would be a valid number, it would be a real number, and moreover it would be bounded between minus 1 and 1. So this would mean you can multiply both sides by x squared, well all sides, 3 sides, and then you take the limit as x approaches 0. Limit as x approaches 0. This will give you 0, and this will give you 0. So we have this limit is less than or equal to 0, and at the same time it's greater than or equal to 0. The only way for that to happen is if it's actually equal to 0. So that's a very common example to use, by the way. X squared times sine 1 over x has a very nice picture. So it's like it's bounded by like an x squared and then a minus x squared. But then the function itself oscillates because of the sign between these 2 values until it starts. It's a very interesting function. You often see that one in textbooks when they're doing the squeeze thing. It has a nice little picture to go along with it. So yeah, that one actually approaches 0 as you zoom in on 0. It doesn't make sense at the origin, right? So it's not defined here there's really a hole at the origin, but really you get as close to the origin as, you get arbitrarily close to the origin, even though you never make it there. And here's an example with a limit at infinity, but the idea is the same. So we know that sine x is between 1 and minus 1. This implies I can divide 3 by x for any non-zero x. X is going off to infinity, so it's going to be a very large positive number, so I know it's not 0. And then I can take the limit as x approaches infinity. And again, the answer here happens to be 0. These are doing simple examples. And so, the answer to this one is also infinity. This is also one you could figure out because it's bottom heavy. The bottom is a polynomial, the top is a function that oscillates between minus 1 and 1. So the denominator is going off to infinity, and the numerator is very small. So the denominator is very large in comparison to the numerator, and so it would go to 0. That should make a lot of sense. So yeah, A, B, and C, they were all using the squeeze theorem, and we were taking advantage of the fact that we could bound our trig function sine and cosine. Any questions on using the squeeze theorem to find a limit? Okay, and again, how do you know when you should be using this? Well, you need to look for it. Remember in our strategy in approaching limits, there's a step where you're specifically considering this. So if you see a trig function show up, you're going to see, can I use a squeeze term? And you see if you can work it in. Or you would use the special trig limits, which we're going to be doing here. So maybe someone else can tell me what they did for D. Okay, you can go anytime. I'm ready. D. What do you guys try? Were you the only one who did? Did anyone do these problems? Okay, what did you do for D?
I multiplied the whole thing by 5 over 5, because it's 1.
Okay, why?
Because if you can get sine 5x over 5x, that's equal to 1, because sine x over x is 1.
Sine x over x is not 1. What rule are you thinking about?
Well, the limit as x approaches 0 of sine
The
x
limit
over
as
x.
x approaches 0 of sine x over x.
Yeah.
Okay,
You know what
so sine x over x is not 1.
Okay. Well,
So we know that the limit
I'm not gonna
as x approaches 0 of sine x over x is equal to 1. When your x value is approaching 0, this guy is equal to 1. We know it's not always 1 because we just showed that when you're going off to infinity, this thing converges to 0. Right? So it starts at 1, but then it keeps leveling off, which is not equal to the function 1. So we know that. Now, remember what I said, it's very important that you follow the rules exactly. It's important that this is an x and that is an x. In other words, these two things must be equal. In other words, the fact that there's a 5x in the sign and there isn't a 5x in the denominator matters, right? Pay attention to details here. So, in order to get the 5x in the denominator, you did trick that math people often use to cheat their way into a situation that they're not in. Multiply by 1 in a weird way or add 0 in a weird way, very common techniques. So what you can do, as you mentioned, is you can multiply by 5 over 5. So that's multiplying by 1. Okay. And then what did you do?
So I took the 5 in the numerator and I pulled it out in front of the limit.
Mm-hmm.
And then I did the limit of x equals 0 of sine 5x over 5x, which we just talked about being 1.
Right.
And then that
So
would just be-
we didn't actually do a rule for that yet, but just doing the plug-in rule would give you the same result here. But yes, you can pull this 5 outside and then move this 5 underneath. And by the way, that idea, the fact that you can shift things when multiplying fractions, as long as you keep them in the numerator or denominator where they were in the original, is an algebra skill that I expect you guys to know. Like, you can slide these x's and these 5s around all over the place as long as you keep them in the denominator. The order is not going to matter. So yes, you can move this 5 out. At the same time, move that 5 under. And this behaves like that because the angle inside the sign is the same as the denominator and both are going to 0. And so that is equal to, well, 5 times 1. So no, that's 1. So the answer is actually 5. Questions on that one? All right, so this limit is actually equal to 5. That one. Did anyone attend that one, or you can ask the same person? Anyone else got this one? Julia, did you do it? What did you get? How did you do it?
I multiplied the top and bottom by 6x. And then, so each of those multiplied by tangent of 6x or tangent of 5x. And then I separated it into 3 things. This is probably not the simplest way to do it, but I separated it into tangent of 6x over 6x times 5x over tangent of 5x times x.
Okay, so let's just do it all at once. So multiply by 5x over 5x. And now you start doing your shifting. I can take the 6, move it over here. Take the 6, leave it, take the 6 on the bottom, move it under this guy. So the top one I'm going to leave alone where it is, times, ultimately over here I'm going to have tangent of 6x over 6x, because I shifted the bottom one underneath that tangent. I can shift this tangent 5x off to get 1 over tan 5x. But at the same time, shifting this 5x to the top of that puts me over here, and I'm left with the 1 over 5x here. Okay, that's just me rearranging things to get into a nice form. Now we can take this limit by plugging in. By the way, the x's cancel. So we have 6 over 5. And then what do we get? What's tan 6x over 6x as the x goes to 0?
1.
Right, so this gives us 1. That will also give us 1. And so this answer here is just 6 over 5. So we just multiply and divide by the same thing to get things in a nice form. We can shift things around. Algebra says we can do that. That's how multiplying fractions work. And we can, once we get things into a nice form where we can apply a rule, we just apply the rule. Did you do F?
Yeah.
Yeah. Okay, how'd you do it?
First, I use the sine 2x is equal to 2 sine x cosine x.
Okay, that's the double-ended formula. 2's will cancel. Then what?
Then I, out of the numerator, I factored out a sine x. And then I separated that to be the limit as x approaches 0 of sine x over x times the limit of as x approaches 0 of 1 minus cosine x over x to get 2 different
Okay,
differences.
so this x squared, again, you can do that whole shifting thing. Shift 1 factor of x over here. Right, because just remember that x squared is x times x. So I can just leave one under here, shift the other one over there, and then what happens?
Those are both identities.
These are both special trig limits. This one goes to
1,
1, and this one,
0. So just
0.
0.
And so we have just 1 times 0. The limit is actually 0. Did anyone else actually attend these, but you were just too shy to say something? So, you'll probably do well on tomorrow's quiz anyway, since you actually tried the problems. But I'll give you 6 extra points on tomorrow's quiz, okay?
Oh, thank you.
1 point for each thing you tried. Okay, everyone work on that one. Let me know what you get, and we will move on to. I should tell you the limit laws after that. I mean, technically, how we did it, we don't need to know them explicitly, but it's nice to know them explicitly. So. All right, maybe let's work on this together. What are you thinking? Yeah?
We at least know that it can be 1, like x cannot be equal to 1.
Sure. Yeah, because you you plug in, you divide by 0. Yeah.
So would this be, we use the squeeze theorem here?
How would you apply it?
Well, you have to find its boundaries first.
Okay. How would you find those?
It would be negative 1 and 1.
For what? How did you get the negative 1 and 1? What are you thinking? Because these are in the same. Remember, this is an x squared, this is an x, so they're not exactly the same. Yeah?
Can you factor out the x squared minus 1 into x plus 1 minus 1?
Sure. That might be something I would try. So that's x minus 1 times x plus 1. Okay, now what?
Can you cross out take the absolute value of the denominator? Or
Okay, what is that? How do you do
is
that?
that x plus 1?
Yeah, that's not how the absolute value works. Yeah, that's what makes this one a little bit tricky. The fact that this is an absolute value. How do you deal with that? Anyone else have ideas how you deal with the fact that one of them has absolute values, the other one doesn't? And we're going to 1, so the absolute value is going to 0. What do you know about the absolute value function when it's approaching 0? Oh,
No, when the absolute value is approaching 0 for the
yeah.
is it undefined?
How does it behave? It's not undefined.
No.
It's absolute value x. When you see that, what do you think about?
Maybe I'll fix it like that.
Correct? How's the picture going to help you find the limit?
Yeah.
Because that's now it's not just x, it's x minus 1. And technically you can shift this one to the right by 1. It's probably beneficial to think about the absolute value the other way. How did we think about the absolute value algebraically? how did we define the absolute value? What does it mean to be an absolute value? Yeah?
Well, that could be, like, x could equal plus or minus x because of the absolute value.
So either x if x is greater than or equal to 0, or minus x if x is less than 0. It's kind of optional who you put the equal sign on. Different people put it different places. If it bothers some of you, you can actually just put in a third line. That's basically how you want to think of the absolute value in terms of algebraic terms. And by the way, it still applies. Again, as I mentioned before, every formula is a template. It's just a way to think about something, which means if I don't have x and I have some random function inside absolute values, how do you think I should think about it? You pretty much go to that formula, which is your template. Everywhere you see an x, you now replace it with f of x. So the absolute value of some random function is going to be that function as long as the function is positive. The absolute value is not going to do anything because it's already positive. It's going to be 0 wherever the function is 0, and it will actually negate the function whenever the function becomes negative. Right? Now applying that here, you end up with you see an absolute value, and you're approaching the point where that absolute value is hitting 0. You need to understand, at that point, things split. Now it depends on whether you're looking at the positive side or the negative side. So now this one limit becomes 2 limits that you have to consider. It depends on if you're coming from one from the right side, in which the inside expression is going to be positive, and so the absolute value is just going to give you the function back. The other option is you can approach from the side where the 1 is, when you're a little bit less than 1, approaching from the left, in which case, right, so you're like 0.99999, in which case 0.99999 minus 1 is negative, so the absolute value is going to take the negative of that function. So there's a negative sign. So now, you just deal with each of those separately. Right, so factoring seems to be the right first step here, but then you have to remember how to deal with these special functions. And give you the definitions because you need to use them, and you need to, again, think of them as templates. All your definitions, they can morph to mean something depending on the problem. So you really have to know the definitions very well. So now, this would just cancel. And so in the top, we'll get the limit as x approaches 1 of this guy. And in the bottom, this cancels into that a negative time, so we get x approaches 1 minus this 1. So that means, what would I get here?
2.
Well, 2. And here?
-2.
Minus 2. And I would get 2 if I'm approaching 1 from the right, and I'll get minus 2 if I'm approaching 1 from the left. Conclusion?
Doesn't exist.
Limit does not exist. Because the left and right sides don't agree. So remember how to deal with the absolute value function. Knowing that definition is very important. You're always worried about when an absolute value hits 0, because on either side of that, It's going to change what the function is doing. Now, in the event that you're approaching something where you're not close to 0, you don't really have to worry about this. You just take whichever definition applies. So, to tweak this example a little bit, if I ask you, what is the limit as x approaches 2 of that same function? Then I wouldn't have to split that in 2 because the absolute value isn't approaching 0. It's kind of just a plug-in thing, right? So you can actually just think about this. It's exactly the same as that function. Because when x is 2, the inside here is positive, the absolute value just gives you the inside. And now you don't even have to factor anything because the denominator is not 0, you simply just plug in 2. So in that case it would be 3. So the thing is here, squeeze theorem wouldn't work because it's not really bounded. The ends behave like these two functions. This one is going off to infinity, that one's going off to negative infinity. So you have to remember, for the squeeze theorem, you have to be able to bound some function between two other functions whose limits exist and give you a number. So the fact that in this case the right side was going off to infinity and the left side was going off to negative infinity, squeeze theorem doesn't apply because, sure, the answer is somewhere between infinity and negative infinity, right? It's not very, you can't really apply it. Yeah?
With the one example we did earlier, when you drew it and you bounded it by positive and negative x squared, and then you drew the sign oscillating, is the denominator like the one that you like draw with like, that you drew with like the bounded and then, do you know what I'm saying? Like, if you wanted to draw this to like get a visual aid, would this be like bounded by the absolute value of x minus 1 and then draw x squared minus 1 like within it? Or does that make sense?
I see what you're saying. I'm not sure off the top of my head what the graph of this would look like. It would look, well, not true. We know what it would look like. It's a piecewise graph.
Right.
Where on the right side of 1, it's x plus 1, and
Yeah,
on the
it's
left
just
side
two
of 1,
linear.
it's the other one.
Yeah.
So the graph of this one, at 1, on the right side, it would be the function x plus 1. So it starts at 2, and then just goes off in a straight line. And to the left side of 1, it would behave like minus x plus 1. So it would be at minus 2, and then it would go off from that. The other one, the x squared times sine, this one you just have to realize this is bouncing between plus or minus 1. So at any given time, you actually, the outer edges means you're multiplying x squared by positive 1 or minus 1 at any given time.
Gotcha.
Which is why the upper bound is the function x squared, because you're only multiplying by 1 and nothing
That makes
bigger.
sense.
And the lower bound is minus x squared, because you're multiplying by negative 1 and nothing bigger. For anything in between those values, you're somewhere in between.
Okay,
So these are the max and min values that you're going to attain.
that makes sense. Thank you.
Yeah, but for this one, it's a piecewise function. Just again, with the absolute value, break it into, and that would be what the graph is. So had you even done that, if you had looked at this and decided, you know what, I'm going to graph it, you would also see that the limit doesn't exist.
Makes sense.
I do want to mention, basically for the sake of completeness, because if I teach limits and then I don't give you these rules, people are going to be like, what? He never told you guys these rules? And technically we've been using them the whole time. It kind of falls naturally, but it's nice to know what rules actually apply. And later on I'm going to be referring to them when we do certain things. So basically it's what we were using, the fact that you can factor constants out, that limits would distribute to sums, things like that. So limit laws. These are basically the algebraic rules that limits will obey. So, assume the minute x approaches a, f of x equals L. The minute x approaches a, g of x equals M exist and are finite. Things get kind of weird in these rules if we allow our limits to be infinite. So I'm assuming L and M are just real numbers, they're not infinity or negative infinity. So assume these two limits exist for these functions. Also assume C is a constant. Then the following hold. One. You should know that limits will distribute across sums and products. So that is the limit as x approaches a of f of x plus or minus g of x is going to be equal to the limit as x approaches a of f of x plus or minus the limit as x approaches a of g of x. Which we kind of figured out by plugging in, it's the same thing you would have gotten, right? You would have gotten L plus or minus n by just plugging in the values, right? So a limit distributes across sums, right? It also distributes across products in the case that they're finite. In the infinite case, these don't always work in the infinite case. But assuming the limits of each function are finite, the limit will distribute across a product. Right, we use that in our in the trig function examples, right? Where I could think of the limit as tan 6x over 6x separately multiplied by the 5x over tan 5x as x goes to 0, etc. So I can just take the limit of each part and multiply them together, and that will actually give you the same answer. I believe we mentioned this already, but let me just mention it here to make sure. Limit as x approaches whatever value of a constant is just a constant. We did a few examples there. You should also know that limits, you can factor constants out. So if you have a c times a constant times a function, this is the same as the constant times the limit of the function. Limits also will distribute across division. So limits are very nice. They kind of distribute pretty much across both multiplication and division. Not a lot of things do that. Remember, like powers, for example, don't do that. Powers don't distribute across sums, but they do across multiplication. So it's nice to know what rules you're allowed to do with limits. In the case your limits are finite, all these things are okay. At any time you can apply one of these rules if it makes solving the problem easier for you. And this is g of x. So this will be L over M, of course, provided your n is not 0. This will just be C times L. Plug in any of these. This will just be L times M. As well as you can move a limit inside a power. So for example, I have the limit as x is approaching a of f of x raised to a constant power. I can actually take the limit of the inside and raise that to the power. And that will give me an equivalent value. And we can require here that c is greater than 0 to ignore the division signs and things like that. But you could apply that in the denominator in theory. So these are called the limit laws, telling you about the algebraic properties of limits, the things you can do. Limits are pretty nice. As you can see, distribute across sums and products very nicely. Limit of a constant is just a constant, distributes across division, goes inside towers, they have very nice algebraic properties. So, you should be aware of that. I wanted to start talking about continuity, but I think we'll start tomorrow. We don't have much time here. So tomorrow you have a quiz on limits, everything we did last week into this week. And yeah, and then we'll start. So that's in recitation, and we'll start continuity in class. So go study. Make sure you're ready for the limit problem. And if I give you problems to do at the end of class, it is important that you actually attempt them. Okay, we'll stop there.